Welcome everyone to our talk about 20 plus ways to bypass your macOS privacy mechanism. My name is Csaba Ficl. I'm currently working at Offensive Security, and I'm the author of the upcoming macOS control bypasses training. I have an open source app called Shield, which can be used for exploit protection on macOS. I used to be a red and blue teamer for a very long time. Before that, I'm married, have 2 kids, and I love to spend my time in the mountains. Over to you, Wojciech.
Yeah, so my name is Wojciech Reguła. I'm a senior IT security consultant currently employed at Securing. I'm mostly focused on iOS and macOS application security. In my free time, I also run a blog about Apple security, so you can see the link on the slide. You may also know me from the iOS security suite that I'm a creator of. It's an open source Swift library that helps you to make sure if you run your application on a secure iOS device. And recently, I also started a new service that is macOS environment security testing. But coming back to the presentation, so we both with Csaba made joint research about TCC and the security mechanisms present on macOS, and we identified a lot of different ways to bypass the TCC. As this is only a 40-minute talk, we don't have to talk about every vulnerability we have identified. So this presentation will focus only on selected vulnerabilities that I hope and also hopes that you will enjoy. So the first mechanism we want to discuss in order to show you how the TCC works is system integrity protection. It's based on sandbox kernel extension and restricts access to many directories on macOS. It also, as it's called system integrity protection, it protects the integrity, so it will also block you from injecting your probably malicious code to system services that are, of course, signed directly by Apple's certificate. And system integrity protection is also known as rootless. Because on macOS, if you have root, you are not a god. You still cannot do everything you want. So system integrity protection will prevent you, even as a root, to access some directories, to write files to specific directories, or to attach, for example, debuggers to Apple's processes. But what does the TCC stand for? TCC is Transparency, Consent, and Control framework. It makes sure that you have permissions to some privacy resources. So, for example, a malicious application cannot access your desktop or, for example, your address book. Let's take a look on an example on the slide. So I've opened the fresh terminal, and terminal, of course, is an application in the context of macOS, and I tried to list the address book. And as you can see, macOS prompted me with that prompt if the terminal would like to access my contacts. So I can grant the permission or not. If you are a macOS user, you are probably familiar with this privacy tab, and this is the core of the TCC from the user's perspective. You grant, for example, permission to camera to specific applications, or, for example, in the automation subtab, you can give access to one application that will be able to control another application. So yeah, this is briefly about what TCC is, but from the reverse engineer perspective, so from our also security perspective, TCC has a SQLite-free databases. These databases contain the rules, the permission you had granted to the applications. And you have one global protected by the system integrity protection database placed in the library application support com Apple TCC directory. And per every user, you have another TCC database in the home directory /library application support com Apple TCC directory. The first database, the global, contains the permissions to, for example, full disk access. But the second one, the per each user database will, for example, control your camera and user-specific directories like desktop or contacts. To show you that's indeed a SQLite3 database, I connected via SQLite3 binary and selected a few columns like service, client, out value, and code sign requirement. The first one contains the permissions that we had granted to the applications. Client contains in this case, bundle identifiers of the applications that have the permissions granted. They may be also paths to these applications. The out value contains the current authorization value, so if the permission has been granted or not. And the CS-rec stands for code signing requirements. And as you can see, there are quotation marks, and this appeared because the code signing requirements are not printable. So I took one code signing requirement and coded it in base 64 and I have written such a code to show you how to decode this code signing requirement. So on the screenshot below, you can see that you can create a human readable form from this non-printable code signing requirement. Okay, so now I'm passing the microphone back to Csaba.
Okay, so the next big pillar of TCC is all around user intent. This comes into play when the user is showing a clear intention that he or she wants to access a particular file. This user intent is controlled by an extended attribute called the Apple macOS, and it's entirely managed by the sandbox and also protected by system integrity protection. So user cannot just add or delete these attributes. So basically what happens, what is shown here on the screen is, let's say terminal doesn't have access to the documents folder, so the user cannot print out the password txt stored in this directory. But if the user drag and drops the password txt from Finder to terminal, the user shows a clear intent that he wants to access it. So what happens at that point, macOS will grant access to password txt for terminal, and then terminal can print it out. So the way it's managed, again, is through an extended attribute, which is stored with the file. It's called Apple macOS, and basically it contains a list of UUIDs with a particular header. The header is typically number 3, and it's 2 byte long. So the second byte is just 0. Here we can see that the password.txt has 2 UUIDs associated. One is for terminal and the other one is TextEdit, which I use to create this file. Now, it's very important that this UUID is unique to the actual device. So if we transfer this file to another Mac device and we somehow manage to maintain this extended attribute, on that device, this attribute will not grant any access to, in this case, to terminal and TextEdit.
All right, so the first group of vulnerabilities that we wanted to show you are TCC bypasses via plugins. So the problem with TCC is that it validates the entitlements held by the main executable. So if you have applications or sub-applications that are executing their code in the context of the main applications, they will inherit the private TCC entitlements or the TCC permissions granted to the main executable. let's take a look on an example. So we have three actors here: the system application with private TCC permissions that contains plugins. We have kernel and the user space TCC daemon. So whenever the system application wants to access the files from the desktop, under the hood, the kernel will be asked if the permission could be granted. So the kernel will delegate this decision to the TCC daemon, the user space TCC daemon. And this daemon will verify the code signing requirement that you saw in the SQLite3 database of the main executable in order to verify if the permission has been granted or not. If it was, the access is granted, and yeah, our application can access the files from desktop. However, if we have the system application that contains a malicious plugin, what happens? And it turns out that nothing special. It's exactly the same situation. The malicious plugin still executes in the context of the main application, so the TCC daemon will only verify that the parent application, the main application that has the permissions granted. So an example of such a vulnerability was that CVE, and we reached it via changing the NFS home directory. So I identified a suspicious application called directory utility, and I call it suspicious because it had a private TCC entitlement that allowed accessing system policies admin files. When I encountered this application, I started browsing through its directory, and it turned out that it contains a plugin subdirectory, and the plugin subdirectory contains four domain admin plugins, the four plugins, and I wanted to know if these plugins are loaded into the context of the main process. So I've opened the Active Directory and also the Task Explorer, and I saw that in the dilibs tab, these four plugins are indeed loaded into the context of the main application. So I was then sure that, yeah, if I change these plugins, if I alter the plugin with a malicious one, it will be loaded probably to the context of the main application. So after that, I started using the directory utility, and I saw that it has access to changing the NFS home directory. And I started thinking on how this could be abused. And I immediately thought that the TCC has the per each user database, right? So the TCC has to somehow know where the user's home directory is in order to determine the SQLite3 database. So I reversed the TCC daemon, and yeah, indeed, it had the user home directory method. And in the body of this method, I saw that it's using the getPowerUID function. And this function has the home directory entity. So I started thinking about, yeah, but where that function gets the information from. And in the man, you can read that it obtains information from Open Directory daemon. So I was almost sure that if I changed it via the directory utility, it will have an influence on TCC. So I confirmed that, and here we can see our exploitation scenario. So at first point, we have to copy the directory utility to a location that will not be protected by system integrity protection. So we will be able to alter the plugin. Then we will inject a malicious plugin that will be executed in the directory utilities context with, of course, the private TCC entitlement that allowed us to modify the system admin files. Then we have to prepare a fake TCC SQLite3 database with the fake permissions. After that, we modify the NFS home directory. So now it will be pointing to our fake location that TCC will resolve in the end to the fake database with the fake permissions. And we then have to restart the TCC daemon. So it will load our fake database based on the new NFS home directory variable. And of course, we achieve the full TCC bypass. So let's take a look on the demo. We are now confirming that we don't have access to the address book. So now let's try to open the exploit. It failed because we need root to change this NFS home directory entry. And as you can see, it has been changed to another one. Now we have to restart the TCC to make sure that the new fake database will be loaded. And once again, let's kill it to be 100% sure it has restarted. And as you can see, once again, we now have access to the address book. So yeah, we have successfully exploited TCC. Another example of TCC bypass via plugins is via Core Audio Daemon. So I identified yet another executable with suspicious permissions, and Core Audio Daemon had two suspicious permissions. The first one was TCC Manager that allowed to change the rules in the zip protected database. And the second one was desirable library validation. So macOS won't verify if the library was signed with the same certificate. So in this example, the exploitation scenario looks as follows. So at first, we create a malicious macOS bundle with driver extension that will be our plugin. We plant it in HAL plugins directory. We start the core audio daemon, and yeah, once again, we can fully control the TCC daemon. Let's take a look on the code. So I didn't want to, manually write all the code to that will change this permissions in that SQLite3 database. So I decided to reverse the private TCC functions, and I found one that will make this job for me. So I externed it, and based on this function, I gave the full disk access permission to the terminal. So let's take a look on the demo. We once again verify if we have access to the address book. We don't have. Let's try if sudo has it. No, because as I told you before, sudo doesn't make you a god on macOS. But now let's try to open the exploit. As you can see, the terminal has appeared in the full disk access subtab. Now we have to restart the terminal. And let's now verify if we have access or not. And wow, we have access to the address book. That means that we have yet again successfully pwned the TCC. All right, so now let's go to the second group of vulnerabilities, the TCC bypasses through process injections. So we, once again, will be executing code in the context of the entitled application. But usually, as I told you on the system integrity protection slide, we cannot inject our code to the Apple signed apps. But it's not 100% true. There are exceptions, and one of the exceptions is the Apple security get task allow entitlement that will allow us to get the task port of the remote application. So I've identified that there is an exonctl executable that contains the private TCC entitlement and also has the get task allow entitlement, another suspicious one. So in order to create a simple proof of concept, I proved that if you inject via low-level debugger to the exonctl, it succeeds. So as you can see, I tried to do a backtrace and it succeeded. So yeah, we have the task port of the Apple signed process with the private TCC entitlement. So yeah, yet again, group of the vulnerabilities on how to bypass TCC. And this group of vulnerabilities is especially problematic because a lot of third-party applications are vulnerable to process injection techniques, attacks. So if you download a third-party application on your macOS and you give it the TCC permissions, you have to keep in mind that malware can abuse that application. And the sad fact about it is that Electron applications are vulnerable by default. So yeah, I'm sorry. And we both with Chaba, we have found a lot of different vulnerabilities in different third-party applications. You can see that Firefox is still unfortunately vulnerable, Streamlabs, OBS, Signal, SnagLT, but there were many, many more third-party applications. If you are curious on how you can exploit the Firefox, I'm encouraging you to read my blog post about it. So I'm passing the microphone back to Chaba.
Okay, so let's continue with the third group of bypasses for TCC, and those involve the mount operation in some way. So the first vulnerability I want to cover, I discovered last year, and it involved the mount APFS utility, which we can use to create snapshots. So the APFS file system supports the snapshot feature, which basically allows someone to make a snapshot of the file system, and then if any changes happened later on, those can be rolled back to last known good or bad state, basically. But what we can do with these snapshots is we can mount them somewhere on the file system. So we can create a directory, for example, temp snap, and basically remount the entire snapshot and toss the file system into that location. Now, snapshots are read-only, so they cannot be written to, but we can still read every file through a snapshot. And with us mounting it to a different location out of the standard, what that means is that location will be outside of the scope of the TCC protection, and we can access every user file through the snapshot. But to make it worse, we could use the no owners flag during this mount operation, which means that we can mount the snapshot the way that it will be seen as we are the owner of every file. So if there are multiple users using the same macOS system for any reason, basically what we get is read access to every other user's file. This worked even with being a guest on the system. Now, what Apple did is they tied the snapshot mount operation to full disk access role, which basically meant it pointless. But unfortunately, it's not a perfect fix because let's say we grant terminal full disk access because we need it, and I think many power users do that. What happens if a low privilege user or a guest opens up terminal? They can still perform the mount operation with no owner, so they can still access other users' file. This is a problem, but Apple decided not to tackle that. The other bug was fixed this year, and it also involved mounting. So we discussed that the user TCC database file is located in the library application support com Apple TCC directory. There is a tcc.db database file inside. Now, macOS properly protects this file, so we cannot read or write into this file, so we cannot modify it and add custom rules into that. So that's good, and we can't even modify the directory itself. But we can mount over this directory, which means we can create our own image, create our own TCC database file, and mount it over the com Apple TCC directory, restart TCC, and at that point, TCC will read our own file. And that basically grants us full TCC bypass. And here's the demo of this, showing first that we don't have access to the documents folder from terminal, and then we run our exploit, which will perform this mounting and restart TCC, and then we can list the documents folder, so we gained access. The fourth big group of TCC bypasses involves some application behavior. So on macOS, as we saw, there are many applications that can access private files because of their entitlements. And there are also apps that move files around when they perform some operations, and some applications do both. So even if we cannot inject a code into this application because it's properly protected, maybe we can convince it to move files for us to a location of our choice. So what happens in this game? We have two players, the malicious application and an application which has access to private files. So comes our application and discovers that, hey, the other application has access to private files. Yes, and then our application will perform some operation and ask the other process to move those files to somewhere else. And the other application will happily do that. And we can be nice and thank him for that. So the first vulnerability of such is related to the Notes application. So the Notes application stores all of the notes in a not TCC protected location. So notes are not considered as a private documents by Apple. And what we can do is open a file with the Notes application, and if it's a binary file, the application will automatically attach it to a new note. And this new note, along with the attachment, will be stored inside the Notes directory. Now, we can see if we inspect the Notes application entitlements that it has quite a few privacy exceptions. It can access the address book, calendar, and the reminders. So what we can do is basically open the default or the main address book database with notes. And as it's a binary file, it's a SQLite database, it will attach it to the notes. And then if we go to the library group containers, group com Apple notes accounts, we will find this file there. The next vulnerability is concerning the app translocation service. This could be also a mount related bug because it involves mounting as well. But I classified it as a behavior stuff. So the app translocation service was introduced by Apple to fix a vulnerability found by Patrick Wardle to bypass Gatekeeper. And what it does, if we download an application and run it from the downloads folder or from the folder where we downloaded it to, for the very first time, it will make a null FS mount of that application inside the temporary directory. A null FS mount basically means that it will map the application to another location on the file system and the entire directory structure under it. The destination is typically in the tempdir app translocation /d/d and then the application name. This library is actually open source in the security bundle, and it's in the libsecurity translocate library. And the binary responsible for app translocation is the USR libaccess LSD file. Now, if we inspect its entitlements, we find that once it has a null FS entitlement, it means that it can make a null FS mount. Actually, this is the only application on the entire system that is allowed to do null FS mounts. Additionally, it has also full disk access rights. It can access every file. So what we do in this case to exploit this behavior, we add a quarantine attribute to our library folder. For example, we can do it with other folders as well. And then call the Apple Security Translocation XPC service and basically ask the translocation service to translocate the library folder. And what it will do, it will happily do that and map it to the tempdir app translocation DD library. And through that mount, since that path is not under TCC protection, we can access, again, every private file, again, read-only, but it's a bypass. Here we can see a snippet of the exploit. So we first get the home directory location and the temp directory location. We build our paths that is required for the XPC service. We populate an XPC message, a dictionary, and then we pass this message to the Mac service. Because of the translocation service is open source, it was actually quite easy to build this up because there is an XPC client and I could use that. Now here's a demo of this exploit. So we will try to list the messages with a folder which contains the iMessages of the user, which is protected by privacy. Then we will run our translocation exploit, and we can see it's mapped to this long directory. And if we take it and check the messages, we will see that the chat.database is available for us, which contains the messages. Now, the last big group is not really a bypass, it's more like leaks. Basically, Apple thought that private info is located only on these certain locations, like the address book folder, the messages folder, the documents folder, and so on. It turned out that it's not true. So private information or bits of information are all around the file system. So how to find this? Just grep around. So what I did, I grep for an email address, I grep for a phone number, some iMessage content or email content inside my entire library. And there were multiple results of this, which resulted in plenty of info leaks. So sometimes it was as simple as file names, but that's considered as our private info. So these are resulted in the CVEs. In some cases, I found contact information with phone numbers, email addresses. In some cases, it was family contacts with their birth date. And also, probably the Knowledge C database was the most fruitful because it contained full iMessages, contact information, and so on. Interestingly, the quarantine database, which contained the full download history back to really long time, Apple didn't consider it as a private info, so they said that won't be fixed. Although it can still reveal quite a few information of what size you visited, downloaded from, and so on. And these are the ones that were fixed, but there are more to come actually in the upcoming months. So as a closure, let's also talk about Apple's security bounty program. So they actually have a category for privacy bypasses, which can range from 25K for small amount of leaks up to 100,000 USD for major bypasses. We can't reveal exact payouts, but these numbers are pretty much correct. So Apple is really fair in these terms. Unfortunately, that's probably the only good point of the program. They are really fair and they will pay what is promised, but bug fixes are often really slow, especially if it's more like a design issue. Sometimes they can range from being fixed in 2 years. So there are some bugs we reported in Catalina and will be only fixed in Monterey. There is a lack of communication, so often it feels that we send them an email and no one reads that. Hopefully that's not true, but it would be nice to get some feedback more often. Probably the worst part is the actual decision for the reward, which can take really long time, over 7 months. Both of us have vulnerabilities that were fixed with the release of Big Sur and still not decided if we will get a reward or not. So as a conclusion for the entire talk, we think that the entire effort with the privacy protection is really good. And it's way beyond many other OSs that don't do that. And it's a step in the right direction. So others should do the same. Still, there are lots of issues around that, but luckily Apple is fixing all of these and takes it seriously. Now, probably one of the major issue is that too many Apple binaries have exceptions to access private data, which opens up the road for abuses. And the other big issue is that many third-party applications, especially Electron applications, are vulnerable to injection attacks. So if those applications have access to private resources, then any attacker can access those private resources. And the ASB program have to improve. So thank you for listening to our talk, and we will be available for question and answers in another channel.
Yeah, thank you for listening to us.